Good afternoon. Thank you for coming here on site and online as well. We have many people attending this seminar and webinar today. It's actually the first real seminar in person we're organizing after quite some time. So it's nice to be back in presence. So today we have the great opportunity to have Giacomo Falchetta, and he will essentially walk us through this new tool, Google Earth Engine, with R, which is one of the many tools which are being released to work with geospatial data. And Giacomo, he's a postdoctoral researcher at Ca'Foscari and also at CMCC within the Echeck division. He's an economist and he has been trained as energy and environmental economist, and he's specialized in the topic of energy, water, and he works a lot with high resolution data, geospatial data, to address important questions related to energy, water, and the environment. So this is meant to be a practical session and also quite interactive. We have people online, people on site. So of course, if you have questions, especially those at home, you can type your question in the chat. And for the people here, of course, you just raise your hand and ask your question. We will need to repeat the question because people at home wouldn't be able to understand what you're saying from the back of the room. So you have to be a bit patient, but yes, it's a practical session. So please feel free to ask questions as we go, clarifying questions as well. Okay, thank you, Giacomo. We have, I think we should try to finish by 4, something like that. Yeah, well, 1 hour and a half, 2 hours at max, and. Also, the webinar is going to be recorded. I think it will be available on CMCC website. Thank you, Giacomo, and looking forward.
Yes, thank you, Enrica, and good afternoon, everyone. So just to give a little bit of a structure, so today the session is divided in 2 parts. The first part is a bit of introduction, theoretical introduction of what we're talking about. So what is geospatial data and analysis, and what are the tools to work with it? And then the second part instead will be a practical part where you have 2 options. You can simply follow the content that we show on the slides, which includes the code, some examples, or you can directly on your laptop concretely do the things that I will show. So I will be sharing a link with everyone in the second part where you can download some scripts that we will be using together. So just to provide a bit of context, first of all, what is geospatial data? Probably if you are here, I guess many of you already have experience with spatial data, but just a tiny bit of introduction. So normal data, usual data, it's generally in tabular form, so a structure with columns and rows, so variables and observations. And a very simple way to think about GIS data, spatial data, is the exact same structure, but with an additional variable or column, which is the geographical indication of what we're talking about. So in general, spatial data is like a conventional data table, data frame, but with an additional variable or column with geospatial information, geographic information attached to it. And this information, this geographic information, can be of different types. So broadly speaking, it's divided into vector and raster data. Again, probably familiar to many of you. Vector data is basically points, lines, and areas. So everything that can be represented as a discrete measurement in space. So, for instance, a river, or administrative boundaries. So discrete units of space, which can be point coordinates or lines or polygons. Instead, rasters are gridded structures where you have continuous values over the space, or grid cells, which are regular repeated units over space, and they are more suitable for continuous measurement. For instance, the measurement of altitude over space. However, these two type of spatial data are more or less suitable to represent given type of information. So raster data, continuous data, is suitable for continuous measurement in space. Some examples are population density, temperature, elevation, wind speed, so things that can be measured at any point in space. Instead, vector data is for discrete things, such as river, administrative boundaries, roads, power station position. So this distinction is important to bear in mind. Although then the two type of data can be also interchanged partially between each other. But how does one work with spatial data? In my opinion, there are three main type of software and tools to use spatial data. So we can have the graphical user interface software with maybe some programming capability, but mainly visual. And the most common ones are ArcGIS, which is paid software, or QGIS, which is the open source alternative, which are really nice software, by the way, but they have the limit that they are not extremely easy reproducible or combined with other code. So if you want to do a lot of operations in a like in a loop or for a large amount of data, or if you want to combine these spatial operations in your conventional data analysis routines, they are not extremely suitable, although to an extent it is possible to do so. Then you have programming languages, so the classic data science languages like R, Python, MATLAB, etc., which nowadays are all equipped with GIS libraries to do pretty much everything. So you can manipulate and do spatial operations with programming languages, typing code. But of course, these consume local computer resources. So if you're working with, if you have experience working with the GIS data, you know that data can very quickly become very heavy, and it can be quite slow to process on a laptop or a normal computer if you want to process information over a large area, for instance. So they have this limit that if your computer is a regular computer, you might encounter some bottleneck of computing power. And then you have online computing, cloud computing interfaces, which is something relatively new. It's only a few years that they have started appearing. And the two main competitors are Google Earth Engine, which is the one we're talking about today. And then this very recently launched Microsoft Planetary Computer, which is like computing, which is the rival of Microsoft for this type of analysis. And basically, these tools have the benefit that they outsource the computing power to do GIS analysis on the cloud. So your local machine will not be affected by the size of the data because the calculations happen online. And the objective of the seminar is basically to show how to make the most of option 2, so programming languages on your computer, and option 3, which are these cloud-based interfaces, which, however, generally are operated in the browser, so in a web browser, so you don't really have your traditional or your usual coding environment. So here we try to show how you can combine cloud computing for GIS into your conventional coding activities and languages. Yes.
Giacomo, talking about the third option, are those freely available or we have to?
Yes, thank you. They are completely free for research. So for non-commercial purposes, they are usable, both of them. However, as you might know, you have to make a special request in advance. So you have to ask Google, for instance, in this case, to enable your account to use this tool and to provide some reasons why you need them. But they are quite generous in giving you the permission. I've never heard of someone not getting it. So if you didn't get it by any chance, let me know. So yeah. So Google Earth Engine. Today we talk about Google Earth Engine. So a quick overview of what it is. So it's a free cloud computing service for GIS data. The most simple way to access it, you can see the screenshot here, is to access it through your browser. So you can access it directly through your browser via code.earthengine.org.com, but today we will not use it in the browser interface. Why? Well, first of all, why Google Earth Engine? Because it's incomparable in speed when working with big data. So if you have to do something with large spatial data, any type of operation, from extracting climate information over different countries for many years to I don't know, understanding what is the closest point to a given location for a lot of points. This type of very heavy things that can be useful for researchers, like doing it in Google Earth Engine usually takes a couple of seconds, and on your computer it can take hours sometimes. So it's really, when you work with big data, you can really start to see the value added of doing this. However, also the reason we are doing this seminar today is that this type of tool, it's quite new, and so far it has been mostly used by environmental scientists, and although it has a lot of potential also for our fields like social science, economics, it has hardly been used much by other fields. So it has been a bit remaining specific to some domains, probably because it could look like there is some entry barrier when you have to start using it. It's a bit different from your usual coding or GIS software that maybe you're used to. In particular, because in this browser-based interface, it works in JavaScript, which is a language that, I mean, at least myself, I was not very familiar with, although it's quite simple after all, but it's not something that usually researchers have a lot of experience with. Or it offers a Python API also, but yeah, I don't like Python very much. Maybe some of you use Python. So I use R. So today we will see how to use it with R. But it's technically also possible to use it with Python if you prefer Python. Yeah, so thanks to some independent developer, this R package was created called RGE. And it's basically a binding API to communicate between your local R session and script and the cloud computing of Google Earth Engine. So you can use the power of Google processing directly from your script. And also, big benefit of using Google Earth Engine or this type of tools, you have a lot of data, especially satellite imagery, satellite products, climate data, all this global coverage, historical and future information produced by NASA, for instance, or by the European Space Agency, that, but you don't need to download them on your computer. And this is really a big advantage, because usually if you want to download years of data, you have to download gigabytes and gigabytes, maybe just to crop a tiny bit of area of interest. So instead, they already have on the server a lot of data, so you can benefit from that. And finally, you can combine functions, if you're familiar already with R, that are the typical function to work with spatial data in R, which are the raster package or the SF package. You can make them fully integrated in your coding pipeline. So it's really useful because it's fast, it's efficient, it's replicable and everything. So the objective of this tutorial is to show a bit how to use this R package for different applications. Data availability, yes, you can browse. There is a web page where all the data which are currently in the Google database are listed. You have a lot of metadata, so you can know what variables are there, what time period, what time resolution. So you can just browse this page with all the data and see if there is data that you might need, and they keep adding new data as it is released and published. Yeah, so starting to get to go a bit more on the practical, on the technical part. So Google Earth Engine has a bit special or own lexicon of calling the object, which I introduced before in the beginning of the seminar when I was speaking about raster and vector data. So in particular, images, when you hear about image in Google Earth Engine, image is a raster. So every time there is like a function calling something with image, then it means that you're working with raster data. And image can have different bands, and bands simply means different variables. So one image, which is a net of pixels over an area, can have, for instance, maximum and minimum temperature, so multiple variables. In addition, sometimes you can find image collections. So image collections are simply a stack of images. So if you have ever worked with the NetDF files, it's the same idea. So it's the idea that you have a collection of images, which usually are for different periods of time, different days of the year, different years. But here they're called image collections. Then you have features, and features are instead geometries. So they are vector data, or sometimes what also is often shape files, right? So is a polygon, is a line, is a point, and its associated properties. An example is the polygon of a lake and its associated characteristics like name, water quality, and so on. And finally, you have feature collection, which is simply a collection of features. So it's a set of polygons, a set of points. So as you can see, it's the same type of data, simply in Google Earth Engine, it's called in not raster and vector, but it has a slightly different name. It's good to remember this terminology. And then also the functions. So the function to operate the data have some names which are not the typical ones from classic JS. They are slightly different. For instance, one of the most useful and also that we will be using today is called a reducer. A reducer is a function to collapse, for instance, the pixels of an image, so of a raster, into polygons, so into features. For instance, when you want to calculate the mean temperature over Italy, you will take all the pixels that fall within Italy, and you will then calculate the mean. So in Google Earth Engine, this is called the reducer. So reducer is a way to reduce the pixels into one polygon shape, basically, one or more. So as you can see, there are different terminologies, but then in the official guide, everything is explained very clearly and easily. I will give you some documentation at the end of the course where you can learn more. Another important aspect is the scale. So as you know, raster data, so the images, they always have one specific resolution. It means that they are gridded fishnets, like gridded layers, where every square has the same length across the image. So basically, this is called generally the resolution. It can be 500 meters, 1 kilometer, 5 meters. It is the spatial scale at which the observations are measured. And in Google Earth Engine, this is called scale. But unlike in other GIS tool, the scales, the resolution in Google Earth Engine is determined from the output. So from my request as a user, and not from the input. So what does this mean? It's not very, very intuitive. But this means that basically, when I run some function in Google Earth Engine, I will often have to specify a scale parameter. And this scale parameter is the spatial resolution at which I would like that the calculations are made. So, for instance, when I apply a reducer, as I was explaining before, if I calculate the mean temperature over Italy for a raster, an image, I can ask Google Earth Engine to perform this operation at different scales. So at different levels of detail, let's say. And so, depending on the native resolution, so the resolution at which the data comes natively, and the resolution at which I make the request, Google Earth Engine will do a calculation and resampling, so-called, to adapt the scale of the data to my request. All of this to say that basically the accuracy of the operations that we do in Google Earth Engine is kind of on request. So we can request a very tiny and fine scale, and this means that they will be very precise, or we can use a coarser scale, but this will mean that they are more approximated. But this has a trade-off with speed. So basically, the higher scale you want, the more precise you want to be the calculation, the slower it will be the process. Maybe this is a bit theoretical, but when we get to the practical part, you can see what it means. But in general, when you see scale parameter, it means you have to insert a value in meters, which is the resolution of the pixel at which you want the calculations to be made. I don't know if this is clear to, it's not.
Giacomo, is this scale something which is data specific, or you have the same range of options for all data sets?
Yeah, so every data set has a native resolution, which is the resolution at which the data is measured. For instance, a raster can come with a native resolution of 1 kilometer by 1 kilometer, okay? But then you can ask Google Earth Engine to do it at a scale of 5 kilometers, the calculations, and this will be quicker than doing it at 1 kilometer, but it will be more approximated because it will interpolate the pixels such that to operate at 5 kilometers. If the original resolution is at 1 kilometer and you ask to process it at 500 meters, so at a finer resolution than the native resolution is, you don't get any benefit because, of course, you cannot go better than the native resolution. So my usual advice is to, if you want to have very high precision and you're more willing to wait a bit more, you use the native resolution of the data. Instead, if some interpolation is fine, you use coarser resolution and it will be quicker. But this is a bit, it's more clear when you do it practically. Yeah, so this was a bit the theory. Maybe if you have any question, anything that was not clear until now, you can ask me something. Otherwise, if it's more broad questions, we can leave them to the end. And then in the meantime, once you think, while you think you have questions, if you follow the link which is showing this slide, which is tinycc/rge, and then lower slash, no, how is it called? The lower underscore, thank you, rg underscore course. And you will get a folder where you have script, some R scripts, and also these slides if you want to have the slides later. So, any question? Great. Okay. So, yeah, in the meantime, if you want to practically follow what I will be showing, the requirements is having R installed on your computer, version 3.6 or better or newer. Hopefully also RStudio, a way to use R on the computer. And then you should have made this procedure that was mentioned before. So you should have made in advance this request to activate your Google account, or also CMCC account for those of CMCC, or Ca'Foscari as well, which is based on Google, to enable it to use Google Earth Engine. If some of you didn't do it, it's not a problem now. Like, you can follow the slides, but you will not be able to run the code because you need to have an enabled account. And usually from the request to the moment you get the confirmation, it takes 1 or 2 days usually. So if you do it now, you will have it in a couple of days, the account ready to be used. Yes? Yes. Yes, so the address is tiny.cc/rge_course. Does it work? Yes? So, in the meantime, how to install RGE? So RGE, as I was saying, is a R package, so you need to install it like all R packages. But then also, before using its function, it requires some initial configuration step that I will be quickly showing, and then you're ready to use it. So first of all, you need to install it with the classic R function, which is install packages. But by the way, in the directory I sent to you, there is a script which is called configure, right? Configure, and there you have the lines of code necessary to operate what I'm showing. I will not do it myself now. I will just list to you what you're supposed to do. But then, if you run the script in the repository, in the folder, you have the same steps. So first of all, you have to install the package RGE together with some dependencies, some additional packages which are required, and then you can do this with install packages. And then once you will have done that, you will have to load the RGE package the usual way you load a package in R, which is with library and the name of the package, in this case RGE. And then you will have to set up the environment, but maybe I will give you 1 minute or 2 to install the packages. And you need to be connected to the internet, of course, obviously. And if you encounter some issues, some errors, like if there seem to be complex, maybe after the end of the seminar, you can write an email if you're at home, or send me, or we can talk if you're here in presence. In the meantime, maybe you're still downloading it and installing it, but in the meantime, what are you meant to be doing? Yes, afterwards. So afterwards, you're meant to call a function from the RG package, which is the configuration function, which is the function. This function you need to run it only the first time. So now, when you are installing the package, and then after you complete the configuration, it will be set up on your computer. Because basically what's happening is that to operate the package, you need some dependencies, external software dependencies, which will be downloaded automatically. So once you install the package, you should type the function EE install from the RG package, and this will start a guided procedure to basically install the all necessary dependencies on your computer. So try to do this and see if it seems to work. During the procedure, you're asked if you want to continue, if you're sure, and you have to type yes or respond to some requests, but it's quite intuitive. Do you have a question? Ah, no, sorry. Okay.
They're also online, everything seems fine.
Okay. People are saying.
They're
okay. Okay, perfect. Perfect. Did anybody manage to get this done already, or is it still downloading? Still downloading. Yes. Okay, but so you managed to install the package. You're now at the install stage. Okay, okay, that's. So well, once it will be done, but we can still have some minutes to do it. There is a function to check that all the procedure went right, and is Echeck. So the Echeck command, after this is completed, should tell you everything is set, everything is right, and then it means that the procedure was successful. If instead it gives you some error, some warning, then maybe, yeah, there might be something that needs to be fixed. But I tried it on a clean computer the other day and it worked. So in theory, it should be fine. Let me know. Yes?
I'm in the browser right now. So to the Google.
Yes.
So I didn't get what kind of language it's used. It's used Python and.
So this package, you're in the, okay, that's, in that interface, it's JavaScript. So it's specific functions. There is a very well done guide, but not in today's slides to use directly.
Sure. I was like navigating.
But there it's a JavaScript language. Yes. Yes.
I think
Which one?
second code.
It's library.
No, I think you have to put it.
I have to put the commands.
Yeah, press the
Okay.
and the origin.
All right.
Yeah. Because I run the code, it gave me an error warning message, so I added the parentheses.
And it okay, fine. Thank you. Did you manage to? Did it work? There is some. No, yes. So when to this request of C Schilacci, you have to answer yes. So basically, you have to confirm that you want to install Miniconda. So it completed successfully.
Still running.
Still running. So yeah, it will ask you, do you want to install Miniconda? Could be. So you have to answer yes to the request. that will come up.
Just Y or yes.
Yes, you have to put capital Y, which is like yes. Yeah, it takes a few minutes because it has download a lot of packages. But yeah, so in the meantime, when it will be done, you can first check if everything went right with this Echeck, and then you will have to do something which is instead required at every loading of a new RStudio session, which is
Sorry, excuse me. Yes.
the what? The yes? No, just type capital yeah, capital Y.
Oh, I found
if you type capital Y, it should read it as yes, in theory.
Maybe it's uppercase.
Uppercase capital, yes. It's
Isn't
the
it the same? I was just showing some comment.
yes. Python.
Could it be related to the R version they are using?
Could be related. Could be related to that, or could be related to maybe you see that when it gives you the error, it says run EE clean pyenv. So this comment in the chat, you can try to do that and then repeat the installation procedure. Yeah, anyway, maybe during the webinar, if some people don't manage to install it, it's fine. They can
Yeah,
still
at
follow.
least let's see if at least one person
manages to have it completed.
can.
Yes, you solved it. Worked? No,
Installed. Okay.
it worked.
Okay.
this is what it's given in this definition.
Would you like to install Miniconda? Why? Everything articulate cannot install Miniconda on a path containing spaces. Yeah, but that's fine. Can I? I'm not completely sure why this is happening. Yeah, because what version of RStudio you're using? What version of RStudio is this? Yeah. No, just maybe. No, it's not written here. Maybe here. Let me go here. Help. About RStudio. This is, yeah, it's the old version. This is, I think it's a bit old. I think you should maybe update the RStudio version. I think, but in case if you don't manage to do it now, you can follow and you can write me a question later.
Okay, so apparently several people
Are facing
succeeded.
issues. Succeeded.
Yes,
Great.
right.
Did anyone had issues here, like didn't manage to install or it completed? But that's good. Okay, it's a good. Yes. Yes. Yeah, it takes a tiny bit of time, but.
Oh yeah, I know, but at the end,
it failed.
Okay, I installed it 2 times and error inequality failed. Sì, sì. Maybe there's another
Yeah.
library that I should have installed before that is useful for Nikon. Cioè, magari c'è qualche pacchetto pre-Nikon.
No, in teoria no. Did anyone also manage with the Mac computer here? Yes? Yeah, so I don't think it's the operating system issue. We can try later, maybe. Okay. Sorry.
Okay.
Okay, so I guess that we can proceed, and then for those of you with the residual issue, you can follow the slides, and after the end of the session, we can try to solve the problems in case. So, as you saw maybe already from the script, after the EE check, you have to go with EE initialize. And EE initialize is a command that you have to run at the beginning of every R session in which you want to use RG, Google Earth Engine. So you have to load the RG library and then run EE initialize. And EE initialize will, the first time you operate it, it should open your browser, Google Chrome or Firefox, whatever, and ask you to log in into your account. And of course, that time you should use the account that you had activated. So your account which you made the request for using Google Earth Engine. Otherwise, it will not work. So make sure you're using the correct email address. And then it will generate a token, a code, and you will have to paste this token from the browser into the RStudio, and then it will say, okay, it's activated. Maybe try it with EE initialize and see if it works. Yes, great. Okay, well, in the meantime, I will continue a bit with some basic functionality of the package, how to use it, basically. So in the RGE package, all the functions have the prefix EE. So if you start, after you load the RGE package, if you type EE into a script or into the console, there will be the EE, actually lower dash. You will have the auto completion that will show you the list of all the functions that exist in this package that can be used. And then by typing EE $, you will then have access to the whole Earth Engine API. This is just to give you an overview. If you want to have an overview of what are all the functions, you type EE $, and you will see image, feature collection, all these things that I was showing before. This is more useful if you want to explore everything which the package contains. In addition, for those of you already familiar with R and with tidyverse, RG is pipe friendly. So there is this pipe operator, which is used to combine multiple lines of code in one single block, and you can do this also with the RG function if you're already familiar with R. And in addition, you can also, but this is just to mention it, not because you have to do it now, but from RG, you can also request to download data from Google Earth Engine. So you can, yes, process it, data, as we will be showing in the examples, but you can also directly download data from the catalogs that I was explaining before. So in case you want to download an entire data set on your computer, which is generally not recommendable because you can process directly from there, but you can still do it both for feature collections and for images. And you can use EE as SF or EE as raster. And these are to convert these objects from the online catalog into local raster and polygon shapefiles on your computer. But yeah, and also another thing you can do, maybe one question that came to your mind is, okay, the database which is available online is excellent, it's full of useful databases, resources. But what if I have some data, some own data, some custom data that you would like to work on, but it's not on the server? Can I upload it? Well, yes, you can upload your own data on the server, and you can do this both for vector data and for raster data, but it's slightly different. So for shape files, for vector data, it's very, very straightforward and easy to upload them on the Google Earth Engine and then use them directly in Google Earth Engine. I don't know, an example, maybe you're working on a project where you have a very specific boundary that you want to carry out the GIS analysis in. It can be, I don't know, the Venetian Lagoon, for instance, and you want to work on the Venetian Lagoon, and there is no Venetian Lagoon shapefile already in the Google Earth Engine archives, so you can simply upload it to Google Earth Engine and then use it. And to do that, it's very easy, because basically you just need to read your shapefile in R as you would read your normal shapefile, like the read SF function, usual. And then you simply type SF as EE, and this function will convert your local shapefile into a Google Earth Engine filter collection on the cloud. So it will upload it and ship it to the cloud. Yes, question?
I don't know if you can answer that, but what about the property of the data you are uploading?
The property, you mean the privateness and...
Yeah.
Yeah, so by default, when you upload something on Google Earth Engine, it's not made publicly available, so it will not be visible to everyone unless you then manually put it public.
So you maintain the property?
Okay, these are two different things. So the publicity of the data, so the fact that anyone on the internet can access it, by default, it's not enabled, so it remains visible only to you until you decide to share it with someone manually. The property, I am not fully sure, but my intuition, but I might be wrong here, is that Google can then use this data, okay? But yeah, I didn't explore all the copyright and license information, so you can read it. But my intuition is that maybe Google can actually use it, but not anyone on the internet can see it. Yeah, okay. So as I was saying, for shape files, it's very straightforward. Instead, for rasters, it's a bit less straightforward. Why? Because probably Google put some restrictions, because raster files can be very heavy often, you know. So maybe they don't want anyone to dump their collection of raster data on the cloud and accumulate a lot of heavy data. So basically, it's a bit more tricky to upload raster data on Google Earth Engine, and there are two ways. So I made this script, which you find in the folder, in the zip folder, which is script upload your assets, where you can see one way to do it, which is it looks like straightforward, because it's like with the vector, but it's raster as EE. So basically, you will first load your raster and then use raster as EE. However, in this case, you will need to specify an option which is called bucket. And what is this option? This option is basically a request to provide a Google Cloud Storage space, which is a space where this data can be hosted. But this Google Cloud Storage is not as easy as Google Drive, and it's not free also, you have to pay for it. This storage space where you can upload your raster data. So if you want to upload your raster data in a line of code, you cannot do it unless you first activate this Google Cloud Storage and pay. And this is beyond this seminar, so I will not go into the details of this. But as an alternative, you can instead do it manually via browser. So if you go to the code.earthengine.google.com, which is the web-based platform for using Google Earth Engine, there you can, there is a upload section where you can upload data, raster data for free, but it's manual. So if you have a lot of files, it's painful, it takes time, it's not automatic like running one line of code. So it's good, it's a good option to go if you want to upload one raster or a couple of rasters to then use them, you do it through the browser. But if you have a lot of data, then you should consider using this Google Cloud Storage. But first you have to activate it and pay some money to do it. So, but the database of online is so big that most data needs, I think, are satisfied in terms of climate, land, agriculture, environment. There is a lot already online. So check carefully all the data before thinking about uploading your own data. Yes.
There is a question. Is there a memory limit for uploading features in the cloud?
Like a space, I'm not sure exactly of what is the space limitation, but it's very generous. So in my experience, I uploaded a lot of data, a lot of shape files, of polygons, and I've never reached a point where they told me you have a limit. So I'm not sure what is the limit, but it's generous. So I don't think with normal use, I don't think you will face a bottleneck very soon. With the rasters, you have this issue that to upload your own data, you have to either do it manually or go through Google Cloud Storage. But anyway, this was just to say that it's totally possible. Google Earth Engine is not only for their data, but it can be also with your own personal data. You just need to provide it to the server first. Yeah, so now maybe we can start looking at the practical or on some examples of why it's very nice and useful to use this tool. So the first example is on precipitation data. And you can find, there is the script again in the folder I shared. So the script is the script precipitations. And we will be extracting historical rainfall over Venice and in different fashions, so for different time periods. So you will see how quick it can be to do this type of things. So if you open the script, you will find the same steps that I will show in the slides, so you can run them independently. I will just present the code and explain what it is doing, but then you can find the script to run everything. So the first,
just sorry, Giacomo, before you
yes,
go ahead, you might want to repeat that before studying RG, you have to sign up to Google.
Yes. So again, clarification. First, you need to request to use this package and these functions. First, you have to request that your Google account or CMCC account or Ca'Foscari account is activated in the list of enabled Google Earth Engine accounts. And there is a sign up link to do this, which is in the web page where you registered for this webinar. And then once you do that, you have to follow the procedure which we just been through. So to log in to your account in your RStudio session. So these two steps are mandatory if you want to successfully run this code. And then you're able to do it. So in this first example of precipitations, we first create a bounding box over Venice. This I'm doing it. It would be maybe more precise to upload a polygon of Venice, but here this is a simple way so that I don't have to upload any polygon. I just give 4 set of coordinate points and I create a square box over Venice. And in this example, this will be our area of interest just because we are in Venice right now. So with EE, you see the EE operator is the beginning of every Google Earth Engine function, so EE. And then you will say, since we are creating a geometry, it will be EE at $geometry and $polygon. This is a way to create a bounding box, basically. And then what we will be doing, we will be extracting from the Terra Climate dataset, which is a dataset of historical climate and water dataset, and it provides data at 4-kilometer native resolution. How did I get this information? I got it from the Google Earth Engine dataset database. So if you follow this link, which you can also find in the slides, you will see that every dataset which is available on Google Earth Engine has a specific page, web page, with documentation where you can know what is this data, where it comes from, what is the resolution, what is the time period it covers, its data sets, what are the bands, so the variables that it measures, and so forth. So if you follow this link, and for every dataset you have a link of this type, you can get all this information. And here today, in this example, we use this Terra Climate historical precipitation product. There are alternatives, it's just an example. So first of all, we need to import the dataset in our session, right? In our R session. So to do so, we will use the EE $image collection function. So this is where we load the image collection, which is already uploaded on the Google server, into our R session. So basically, image collection, and then we put in commas the path to this dataset. And where do you find the path to every dataset? You find it exactly in those pages which every dataset had. Where you attached, you also find what is the path to that data. So once you browse,
you find it directly in Google there?
Yes. So if you find this, if you follow this link here, like developers.google.com, Earth Engine, etc., you will arrive to a web page with all the dataset. Or also, if you're using the web-based JavaScript version on your browser, there is a search box where you can write, start writing, I don't know, precipitations, and you will have like a normal Google search, but with the data sets that are available on Google Earth Engine. And so every data set has a path. And in this case, the path is this Idaho app score / Terra Climate. So you can copy paste it here, and with this function, you will load it into your session. And then you can see I'm using a pipe operator because I'm continuing to give instructions to R in the same line of code. So here I'm doing filtered. I'm using a filter date function. So filter date is to choose the boundary of time for which I want to load the data. So in this case, I'm loading data for year 2020. So I'm saying filter date between 1st January 2020 and 1st January 2021. And then I also have to select a specific band, so a specific variable that I'm interested. As I was saying, these image collections can contain multiple bands, multiple type of information, these data sets. So here we're interested in the precipitations. So I'm writing, select PR. And where do I understand that PR stands for precipitations? Well, again, in these pages which you have for each data set, you have a band tab. And in this tab, you have all the bands which are contained in the data set. with the name of the band. And for precipitations, the name of the band is PR. So you will specify that you want to get precipitations and not temperature, say. And then we will use some other functions. Then I will not go into the details of every tiny function, but to basically convert this image collection, which is like a set of observations in time of different images, to a single image with multiple bands. This is convenient to then extract it anyway. And finally, I will rename the bands that I just created. So I will rename them such that they are called PP and the number from 1 to 12, because I'm asking, you see, a period of 12 months, and this data is monthly. So I'm asking that you call the precipitation of January PP1, the ones of February PP2, but this is all optional, okay? It's just to make them easier to visualize the data. This you find it directly in the script that I shared. And then in our exercise here, we want to, for instance, to start with, extract the mean precipitation over Venice in year 2020 for every month of the year. So to do so, and we use this very important function that you will be using, I think, very often in Google Engine, which is EE lower dash extract. And this is the way to do these reducers, which I was speaking before, which is like in GIS, sometimes they're called zonal statistics. So it's a way to take raster pixels and apply a function to them within a polygon, within a boundary. So like calculate the mean of all the pixels inside the Lagoon of Venice in our case. And it's very straightforward. So X is the image collection in this case, which we're using. So it's Terra Climate. If you saw before in the previous slide, I defined the object called Terra Climate, this imported dataset. Y is the geometry or the polygon that where you want to extract this data on. So in the first slide, if you remember, we created an object called geometry, which is Venice, is the boundary over the Venice, the city of Venice. And then you will apply this reducer function. So a function which is reducing the mean of all the pixels of the rain dataset over Venice. But then here you see it's EE slash dollar reducer dollar mean, but it could be sum, it could be maximum. So it's a function, and there is a whole list of functions then you can see in the documentation that you want to apply to extract the data. So if you run this command, it will be extremely quick and it will extract for every month of the year the mean value of the precipitation dataset. And after I added some line of codes where you basically reshape the data. So it will come in a wide format. So you have one column for each month of the year, and then to make it easier to plot, I will reshape it too long. But as you can see, this is not spatial data anymore. It has become a normal tabular data, which is the statistics that you extracted from the raster data. So after, this is just normal data processing pipelining, and you can use your favorite function that you're used to use if you use R. And then you can easily plot it. For instance, in ggplot, we will do a line plot, which shows you indeed the mean precipitations according to year 2020. So this is, remember, just 1 year over the bounding box that we designed. Okay. This is not climate data. This is just weather for 2020. So maybe it looks a bit weird because we're just plotting one given year over a small area which is just above the city of Venice. But if you saw how long did it take to extract this data, like really seconds. So, and this without downloading any data on your computer, just everything happened on the cloud and you got the data that you wanted. So this is a stupid example, but it's the minimal functioning idea that how you can get your own data of interest. Just to do something a tiny bit more interesting with the same data set. So we can get, for instance, the long run mean precipitation. So to have more something like, which is more like climate for a series of years. So we do the same, but let's say for the last 10 years. So we run exactly the same codes, but instead of, we change the filter date and we start from 2010, for instance. And this is all the same, so I will not repeat it. We load the data 2010, 2021, and we do the extract operations. As you can see, maybe it takes a few seconds more than the previous one because it's a bit more of data, but it's still quick, like it's still a matter of seconds. And then you can reshape the data again in a very similar way. And then you can use ggplot to plot the distribution of the precipitations over the last 10 years by month over the city of Venice. So now you have more of how the climate in terms of precipitations looks like over Venice, at least over the last 10 years, which honestly I was a bit surprised because actually spring looks quite rainy, like the month of May, and looks quite more rainy than I thought. Yeah, that was interesting. But yeah, by far still the most rainy month remains November, as expected by those living here. Hopefully, because yeah, hopefully this spring it will rain a bit because yeah, we have some drought ongoing here. You know that. So did everybody manage to run the precipitation script without errors? It worked. You plotted this plot. Okay, that's good. I have another example. Maybe I can start it, then we can see if to complete it. Another example is with the CMIP5 data. So future climate change data. A lot of people here at CMCC are working with future projections of climate. So on Google Earth Engine, currently you have available the NASA next GDP projections for future climate change under different scenarios. Currently for the CMIP5 experiment, but the CMIP6, which is the most recent, will soon also be made available online. Yes?
Sorry, Giacomo, before you continue with this example, someone online was asking whether the Terra climate object, for example, can be exported as a PDF.
Yes, yes, yes. Yeah, I was indeed showing before that if you want to download it for any reason, you can use the EIEE as raster function, and this function will download either to your local computer, or also you can set it up to do it on your Google Drive, the actual raster files, which however can be heavy. So it depends on you. If you really want the raw data, you can obtain it with the EIEE as raster, for instance. Yeah, the second example I had for you today is about climate change. So the climate change projections, the CMIP5 data, and in particular, how to extract data for different scenarios of climate change. So there are, the different emission scenarios, and for different climate models. So if we were speaking about climate change, that the projections are made by a large number of models. So, and they can look different from one to the other. So it's interesting to compare them. So you have the CMIP5 script again in the zip folder I shared with you. And we can start, for instance, with importing CMIP5 daily data, so daily projections of climate change. Select a variable that we want to measure, and one emission scenario, and one specific model. So you can choose. So in this case, again, we do EE dollar image collection, but the name of the data product, in this case, the path is nasa.nextgdp. Again, you can find this in the product pages. And then you can define like a start date and end date, just to make it very quick and silly here. I'm extracting year 2030, but it's just to give you an example. Some functions which are explained in the script, which are to calculate, to define the time boundaries that we want to extract. And then, as you can see, using these functions, select and filter, we can filter the properties of the data set to choose the variable, the climate model, and the scenario that we want. So here we are loading the TASMAX variable, which is the maximum temperature. We're loading this MIROC ESM climate model output, and we are loading the scenario RCP 4.5, which is one of the different climate change emission scenarios that have been developed. And then, as we did for the precipitation data, we use the EE extract function to process the data over the geometry of Venice using the mean reducer. And as you can see, before I ignored the scale parameter, but this time I'm putting the scale parameter just to make you notice that I'm doing it. Before, there was no scale parameter inserted, so I think the function gave you a warning like saying, assuming or using automatically 1000 meters, which is the default value. But then you can adjust it. So for instance, I was telling before that the Terra climate come at a resolution of 4 kilometers. So in that case, using 1000, which is 1000 meter, 1 kilometer, is a bit pointless because we're asking Google Earth Engine to process the data at a higher resolution than the native is. So it doesn't make a lot of sense. So in that case, it would be more smart to say scale equal 4000. So the native resolution. This is just to give you a bit the logic. The values, depending on the scale, the values will not change drastically because there is still this interpolation going on. But over large areas, you might have some discrepancies if you choose very different scale parameters because of the approximations that are done if you use coarser scales. So yeah, this is the CMIP5 example. So you extract the data. It takes a tiny bit more than the precipitation data because this is daily data. So it's one observation per day. And then again, you resort the data. This is not GIS, it's just data processing. This data comes in Kelvin degrees, so we convert it in degrees Celsius to make it more easily interpretable. And then you plot it. So basically, for instance, this is for this RCP 4.5, the evolution of maximum temperature over Venice in all the days of year 2030, according to the model that we asked. But here comes the interesting thing that you can do that to get at the same time with multiple models and scenarios. So instead of specifying one single model, you can specify a list of models, for instance. So then I replicate the same code simply, instead of putting the single model name, I put a list of models, and I do exactly the same. And then I extract it over Venice with the same function. I restructure the data. You find everything in the script. And then you produce something like this. So in this case, you can see I have different models. And also, yeah, these different scenarios. Sorry, I forgot to mention. In the second request, I didn't select a scenario. So all the scenarios are being downloaded currently. So in this case, we have two, RCP-4.5 and RCP-8.5. And this is already interesting because you can compare the different models, different scenarios. This is year 2030, so it's quite close to the present. So you don't see a huge difference between one scenario and the other. But if you go further ahead in the future, you will see that this difference, of course, increases. I included additional examples again with this CMIP5 data in the script. For instance, if you want to have monthly data, on the server you have both daily data and monthly data. So you can also have already processed monthly data. So this is another data set. It's still this NASA Next, but it's the 30-day version, so it's like already aggregated at the monthly level. It's another data set available online. And in this case, for instance, I'm just to show that it's a different way to do it. I'm doing it at a specific point. So I'm doing EE geometry point. So it's not anymore a polygon, but it's one single point in space, so a location. And in this case, I will download the minimum temperature, and I will consider multiple models again, but for a much longer time period. So from 2050 to 2060. So for 10 years of monthly data, I will request the minimum temperature. And then again, you use the EIEE extract like before. You process the data and you come up with something like this, which is like for each scenario, the monthly evolution of minimum temperature over the specific locations for the time period in question. And here already you can see a bit more how the different emission scenarios impact minimum temperature, that it's looking different from one scenario to the other. So then it's really up to you, to your needs, to your specific area of interest, variable of interest, to do the request you want. But using the scripts that I provided to you, you can have a minimal think function in example, and then you can use your area of interest, your variable of interest. And there is a lot of data you have for any type of applications. You want climate data, there is vegetation data, such as vegetation health index, NDVI, and there is data for water and water quality. It's really a lot of choice. So, but the basics, if you want to extract data over a location, it's the same. But in addition, you can do much more than what I showed today. This is just an overview. So the resources to see what you can learn and what you can do are the RGE GitHub page. So the page of the package that you're using, where there is, again, instruction on installing and updating everything. And also you can open issues to the developer if you find some issues during your use of the package. They wrote a very good beginner manual, which gives you scripts and examples to learn to do every type of GIS analysis with Google Earth Engine in R. So you can really learning by copy pasting code and adapting to your needs. It's easy. They have a code examples catalog where you can download scripts like the one I provided to you, but to do a lot of things. So you don't need to do almost anything from scratch. Like there are scripts to do stuff which are really online and open, so you can start from them. And then there is Stack Overflow, so this forum of discussion where you can ask questions with the tag Google Earth Engine, and a lot of people are answering quickly to any questions. So I learned the same way, like I learned by using the scripts, the examples. I didn't study from page 1 of the book, like I learned from doing, and it's very convenient. You realize it quickly when you see that the processing time are a fraction of what it would be to download the data from the server, crop it to my area of interest, and then extract it with my computer power, which is not great. So this is the benefit. I would have finished.
Okay, yeah, I came here because there are a couple of questions from people online. One, I think, was related to the latest example. When looking at the extremes like Tmax, would another reducer like max be more appropriate? So I guess the question is, what reducers are available?
Yeah, so reducer is the way in which the pixels which are above my area of interest are aggregated to a statistic. Okay, so I have, I don't know, suppose over Venice I have 1000 pixels and I want to calculate temperature. The reducer tells what to do of those pixels. To calculate, do I calculate the mean of all the values in those pixels?
So you can use any function.
So you can, there is a set of functions, but the basic statistics. So you have mean, you have max, you have mean, you have median, you have count, which is also the count of pixels. So you have, yeah, there are a lot. In the guide, you can find instruction. For the specific question of extreme events, if you say max, what does it mean? It means that it will give back to you the pixel value with the maximum value of all the pixels in your area. So just one, which is the maximum one. So if you put reducer max, but you have to be careful not to make confusion, because one thing is the variable that you're selecting. So maybe you're selecting minimum temperature, and another thing is the reducer, which is the way in which the pixels are combined together. So you can put the minimum temperature as the variable, but then you can use reducer max, which means take the maximum pixels among the minimum temperature pixels. It's a bit tricky, just be careful how you do it, yeah.
Then there is another question, actually, some raster package function like overlay between raster combined with operators such as multiplication, log. Could those be used directly through the EE functions?
Not directly, but to most, like all, I would say all GIS functions like overlay, mask, and this type of operation have an equivalent in the Google Earth Engine language and in the RGE language. And really, I encourage you to look at the beginner manual and the code examples, because there is examples for everything. So you can overlay two images and take the intersection. You can calculate the log of one image. So not always you can use directly the raster function to do something. You have to use the RGE function, but they exist. So in all cases, you find the equivalent. Or if you want to download all the data, you use the function I was saying before. So you say EE to raster as raster, and this will download all the data to your computer, and then you can use it as a raster object. But then the burden of the calculations will be moved to your computer. So it's up to you, but you can do everything. There are the functions, you just need to find them.
Okay, thank you. I think, I mean, people online were enthusiastic about this, this seminar, so thank you very much, Giacomo. So I would, let's say, close here the webinar. You're here.
I'm here, or you can ask me, send me an email. I mean, for the installation issues, I'm not super expert because I didn't have issues installing it, honestly. So first of all, Google the error, and see if you find it like on Stack Overflow. Usually you do, and people with already experienced that error will maybe have asked and solved the issue. So Google the error if you have issues installing it. And yeah, but if you have questions on the script I gave you or on the use of the package, you can drop me an email. I'm happy to reply. And
can you send this file directly to our personal email if I request for this?
Yes, yes. If you drop me an email, I can send you the slides. But they are also in the zip folder. Right? You found them? Yeah, they are in the zip folder on the link. But if you want, I can email them to you. Yeah, sure. Any question? Yeah.
I don't understand where we can explore the information that are available. I understand that there are, for example, temperature data, precipitation, but I would like to know if there are something on nitrogen deposition or soil salinity, so where I can look for available data.
Yes, I don't know if it's visible. Wait, maybe I will, because I was sharing just. So I can just show you quickly. Yes.
Like,
Oop. So this is the Earth Engine catalog. So here you can see all the data sets that are available. You can search, for instance, I don't know, you can search nitrogen. No, you will say, oops. And then you will find the data set which match nitrogen. So I don't know, you have the Sentinel near real-time nitrogen. You click on it. And then here you have the dataset availability, so the time period at which the data is available. You have the provider. You have the link to this data. So what I was showing before, that you have to put then in your code to load it. So in this case, this Copernicus link. And then here some description of the data, what it is. And if you click on band here, you have all the bands which are contained and with some description. So I don't know, total vertical column of NO2, blah, blah, blah. You have the resolution here. This is the native resolution. And then image properties, some other information. So in general, what you need to use the data is the position of the data, which is this one, and the bands of interest, so the name of the band. So in this case, you would have to say select and this string, which is that band that you're interested in, and then you're good to go. So yeah, start from this Earth Engine catalog, and you can find a lot of things. Yeah. Other questions? I don't know. No. Thank you.